Hello, today I want to prove the existence of primitive roots for every prime number p, and I want to start by thanks to one of my viewers who has advised me how to improve my videos. To prove this, we need to use Gauss theorem, which I have discussed in the previous lesson. At first, what is primitive root? We can say that g is a primitive root if g squared, g cubed, up to gp minus 1, all of these numbers give us different remainders mod p. So these numbers must be the permutation of 1 to up to p minus 1 in some order. So to prove this, we need to show that there exists a number g such that g to the p minus 1 equals 1 mod p, and order of g for p must be p minus 1. At first, notice that if we are given x to the n equals 1 mod p, this equation will have at most n integer solutions. If you look at this as a polynomial in prime numbers, this also works for every prime numbers. And now discuss what may be the order of any number, order of any number a for p. If we know that this is k, because we know that for every number a to the p minus 1 equals 1 mod p, from here we can conclude that order must divide p minus 1. So p minus 1 must be multiple of k. And now look at numbers x to the k equals 1 mod p. We know that we will have at most k numbers which has this property, x to the k equals 1 mod p. And now show what type of numbers will it be. If we take any number t such that t to the k equals 1 mod p, we can see that t squared, t cubed, up to tk minus 1, all of these numbers will have the same property. And we will see that all of these numbers will have different remainders mod p. Now look at this number. Because we know that ti to the k equals tk to the I, this equals 1 mod p. So we have proved that all these numbers will have the same property, that if we take all of these numbers into k power, they will give us 1. And now look at that all of them will have different remainder mod p. If ti equals tj mod p, this means that without laws of generality, let's assume that I is less or equal to j, and ti times tj j minus I minus 1 equals 0 mod p. This means that ti is not divisible by p. So this number is divisible by p, but we know that k was the order of t. So g minus I is less or less than k, and so this is impossible, that t to the g minus I must be 1 mod k, because we know that k was the order of t. And now look at all these numbers. For how many of them will be k order? Now we need to discuss t squared, t cubed, up to tk minus 1. If we take any number which is coprime to k and less than k, like take m, t to the m to the k power, this is clearly that this will give us 1 mod p, and for t to the m, k must be the order. Otherwise, we will get that contradiction that m must have some GCD more than 1 with k. And if we know that k equals p times r, not p, q times r, and if we discuss any number which is multiple of q or r in this region, like if n equals q times d, if we take t to the n, then we need to take this number not in k power to get 1. We need to take this only in r power to get 1. So we can conclude that for t to the n, k will not be order. And for how many numbers will we have k as order? We need to count all the numbers which are less than k and coprime to k. And this is clearly phi of k. This is Euler's function for k. And how many numbers may have order like this one? Because we know that every order d divides p minus 1, and for every d we will have at most phi of d numbers who has order like only d. Then if we take the sum of all numbers, d divides p minus 1 and phi of d, this number equals p minus 1. This is Gauss formula, and these are the numbers who has exactly d as an order. But we don't know that all of the numbers has some integer like t who has order exactly k. But we know that x to the p minus 1 equals 1 mod p has exactly p minus 1 solutions because of Fermat's theorem. And if we sum up all the orders of every integers, like f of these, then we must get p minus 1. And if we know that for some d, f of some k, f of k equals 0, then it will be impossible to get p minus 1. This number then will be less than p minus 1. So we have concluded that for every number which divides p minus 1, we will have exactly phi of d numbers who has order d. So for every number we will have phi of d numbers m such that m to the d equals 1 mod p, and d is order for m. D is order. D is an order for m. And now we can conclude that for p we will have phi p minus 1 numbers who will have p minus 1 order, will be their order. So we have concluded that we can always find primitive roots for every number p, and the total number of primitive roots must be phi p minus 1, which is stronger version than the existence of the primitive roots. So this was all I wanted to discuss for today. If you want to consider other theorems, please write in the comments.